Welcome everyone to this lecture series where we are going to solve exercise 5.1 from the book Introduction to Real Analysis by Bartle and Sherbert. So in my previous videos I have already solved question number 1 to 4 from exercise 5.1. So in this video we will solve question number 5 onwards. So let us take the first question, which is question number 5. So this is the question number 5. So as you can see, we are asked to define f is given to be defined on uh, fx is defined as fx is defined as x square plus x minus 6 by x minus 2 for all x belonging to r minus 2. So x is not defined at 2, and we have been asked to define f at 2 such that f is continuous at that point. So to define a function keeping the continuity intact, we have to define the function as the limiting value of at that point. So we if limit x tends to 2 fx exists, then only we can define f to be continuous at x equal to 2. Otherwise we cannot define this. So we have to check. So this question is asking, can f be defined at x equal to 2 in such a way that f is continuous at this point? So to check this, we have to check whether this limit exists or not. So let us see whether this limit exists or not, and we will use the algebra of limits theorem for that. So consider limit x tends to fx. So this is nothing but limit x tends to 2 x square plus x minus 6 x minus 2. So we can factorize this 2 into 3. So this can be written as limit x tends to 2 x square plus 3x minus x square plus 3x minus 2x minus 6 upon x minus 2. So this is nothing but, so when you will simplify it, so this will become x minus 2 x plus 3 upon x minus 2. So this is limit x tends to 2 x plus 3. Now you can use algebra of limits. So using algebra of limits, this is nothing but limit, so using algebra of limits, this is your x tends to 2 x plus 3, and this, so we know this limit, this is 2 plus 3, which is 5. So since limit exists, so we can define f to be continuous. So define f from r to r as fx equal to x square plus x minus 6 by x minus 2 when x is not equal to 2, and 5 when x is equal to 2. That clearly the way we have defined f, limit x tends to fx is equal to 5, which is equal to f of 2. So hence f is continuous at 2. So hence f is continuous at 2. So note that we can define this function f at the missing point. So we're keeping continuity intact only when the limit exists. The limit at that point exists. If the limit does not exist, then we cannot define the function f keeping continuity intact. Okay, so now this question is complete. Let us take the next question, which is question number 6. So this is the question number 6. So as you can see, we are given that f is continuous at point c belonging to a. We have to show that for any epsilon greater than 0, there exists a neighborhood v delta of c such that for any 2 points xy. So instead of taking any point, they're picking any pair of points xy in a, fx minus fy is less than epsilon. So how to prove this? So given is f is continuous at c belonging to a. Okay, and to show that for any, so let epsilon greater than 0 be any real number. So since by definition of continuity, since f is continuous at x equal to c, so there for above epsilon greater than 0 there exists delta greater than 0 such that fx minus fc is less than epsilon by, we will take epsilon by 2 because we will we want to get this desired condition, so that's why we are taking it epsilon by 2 whenever your x minus c is less than delta and x belongs to a. Okay, so this is by definition of limit. So now what we have to do, we have to get this desired condition. So we will pick any two elements in this neighborhood v delta c. So let now for any xy belonging to a intersection v delta of c, and with consider, so we start with this, consider fx minus fy. Okay, so we have started with any 2 points in this set, and we are taking this, so we want to prove that this is less than epsilon, so we have to make use of this star, make it star. So we have to make use of this star. So what we will do, we will take this as this equal to, we can write this, we will use the triangle inequality, so we have to bring this fc in place because we want to use this star, so we will do addition and subtraction of fc, right? So this, by triangle inequality, we will get this fx minus fc plus fy minus fc, right, using triangle inequality, right? Now this is less than epsilon by 2, this is also because this both x and y, they satisfy this property. Xy belonging to a intersection v delta c means that xy belongs to this set, xy satisfy this property, and when any element satisfy this property, then its image satisfy this property. So we have this, so this is less than epsilon by 2 plus epsilon by 2 using star, so which is equal to epsilon. So you can see why we took epsilon by 2 here, because we wanted epsilon here, so that's why we took epsilon by 2 here. So we have proved hence the desired property. So we have completed question number 6 also. Now let's move to question number 7. So I may be going a little fast, but because this is recording and I've already explained all these concepts in detail in my lecture, so I will just solve these questions a little faster. Okay, now this is another question. So this is question number 7. So in this we are given that f is continuous at c, and we are given that fc is greater than 0. We have to show that there exists a neighborhood v delta c of c such that x belongs to v delta c and fx is greater than 0. So this is nothing but this result we have already done in one of our theorems. So I am not going to do it right now. Okay, let me just share with you the theorem that we did, and you can copy the proof of that theorem straight away here and you will get your desired result. So this is the theorem from the book Bartle and Sherbert, from the same book. So this theorem, so using this result you can directly conclude. So either you can copy the proof of this theorem here, so this is similar to this, because in this theorem what we are given that f is a function from a to r, c is a cluster point if limit is positive. So because f is given to be continuous, so limit x tends to c, fc is greater than 0, so then there exists a neighborhood such that fx is greater than 0 for all x belonging to a intersection v delta c. So यहाँ पे a की जगह we have the set of real numbers, so r will be excluded, so we will have that for every point in this v delta c, fx is greater than 0. In fact, let us just write it. Okay, so proof. So since f is continuous at c, so this implies limit x tends to c, fx equal to fc, right? So limit x tends to c, fx equal to fc, and so since fc is greater than 0, so by theorem 4.2.9 there exists delta greater than 0 such that fx is greater than 0 for all x belonging to v delta c and x not equal to c, right? But since at c also fc is greater than 0, so this implies fx is greater than 0 for all x belonging to v delta c, since fc is positive, so for every x in this. So from the theorem we get that x is not equal to c, fx is greater than 0 for every x in this except at c, but at c we are already given it to be positive, so this is there. Or you can just imitate the proof of this theorem directly in this and you will get the result. So instead of using this theorem, you can directly imitate the proof of this theorem here and you will get the desired result. So hence proved. So let us go to the next question, which is question number 8. Okay, so this is our question number 8. So what we are asked in question number 8, we are given a continuous function on R. So f is continuous everywhere on R, and we have been given a set such that fx in this s at every point in s, fx is 0. So that is, it is the 0 set of f, and we are given that xn is a sequence in x that converges to x. We have to show that x belongs to s. So let us try to write its proof. So what we are given? So we are given first f is continuous on R, and second xn is a sequence in S such that xn converges to x. To show, we have to show x belongs to s, that is we have to show fx is equal to 0. So this we have to show, right? Because any element in s has to satisfy this property that fx should at that point should be equal to 0. So we have to show this now. So since f is continuous on R, so in particular f is continuous at x. Now by sequential criteria for continuity, xn converging to x implies your fxn converges to fx, right? This is the sequential criteria for continuity, that if xn converges to c, then its corresponding sequence fxn should converge to f of c. So xn converges to x, so this implies fxn converges to fx. Now xn belongs to s for all n belonging to n. What does this imply? This implies that f of xn is equal to 0 for every n in n, and this implies that your fxn is a constant sequence, so it converges to 0, right? And so this is double star. So by uniqueness of limit, what we will have from star and double star, we have fx is equal to 0, because we have already shown that fxn is converging to fx. Here in star we have shown that fxn is converging to fx, and in double star we have shown that fxn is converging to 0, but limit has to be unique, so both have to be equal, so fx is equal to 0. So hence, this implies your x belongs to s, hence proved. Okay, so we have completed question number 8. Now let us move to question number 9. So in question, let me just copy paste the question number 9 here on the board. So this is the question number 9. So we are given two sets A and B contained in R, where A is contained in B, F is a function from B to R, and G is the restriction of F to A, that is Gx is equal to Fx for every x in A. Okay, so F is a function from B to R, G is a function from A to R, where G is equal to F restricted to A, that is Gx is equal to Fx for every x in A. In the first part we are given that, okay, so in the first part we are given that F is continuous at C belonging to A, and we have to show G is continuous at C. So this is very easy. Given F is continuous at C belonging to A, and to show G is continuous at C. So to show G is continuous at C, we have to use epsilon delta definition. So let epsilon greater than, so we have to choose any arbitrary epsilon. So let epsilon greater than 0 be any real number. Okay. So we have chosen any epsilon greater than 0. Now what we shall have, so since F is continuous at C belonging to A, so for above epsilon greater than 0 there exists delta greater than 0 such that Fx minus Fc is less than epsilon whenever x belongs to V delta C intersection B. Why B intersection B? Because the domain of F is B. Okay, so the domain of F is B, so we have to take this x belonging to V delta C intersection B. And what we have to show? We have to show that Gx minus Gc is less than epsilon whenever your x belongs to V delta C intersection A. Now this mark it as star. Now for any x belonging to V delta C intersection A, consider Gx minus Gc. So we have to show that this is less than epsilon. Now Gx, because your x belongs to A, so this Gx is equal to Fx, right? And Gc is also equal to Fc, because Gx is equal to Fx on A, because G is equal to F on A. So both, because x is in A and C is in A, so Gx can be replaced by Fx and Gc can be replaced by Fc. And because now this x belonging to V delta C intersection A implies your x belongs to B, so because A is contained in B, so this implies this is less than epsilon, using, so which is less than epsilon, since using star. Okay, so we have to use star, and what, using star and the fact that A is contained in B, so that is V delta C intersection A is contained in V delta C intersection B. So if x belongs to this, then x belongs to this, so it should satisfy this property. So that's why we have this. Okay, so hence Gx minus Gc is less than epsilon whenever your x belongs to V delta C intersection A. So by definition of continuity, by epsilon delta definition of continuity, G is continuous at C. Okay, so we have proved the A part of this. Now let us see what we have to do in B part. So B part, we have to show by an example that if G is continuous at C, it need not follow that F is continuous at C. Okay, so this is very easy. You can take the Dirichlet function here. So G you can take on the set of rationals only. So if you take, so this is very simple example. So consider the example for B part. You can take f from R to R defined as fx equal to 0 if x belongs to Q and 1 if x belongs to Q complement, which is set of irrationals. So we know that f is not continuous at any point in R. So we know that f is not continuous at any point in R. This we know. Now define G from Q to R as G is equal to f restricted to Q. That is Gx is equal to fx is equal to 0 for every x in Q. So because its domain is Q, so then for any point C belonging to Q, so let epsilon greater than 0 be any real number, and you can take delta also to be any real number. Then for any delta greater than 0, x belonging to V delta C intersection Q. So because x is belonging to Q, because our domain is Q, so we have to take this intersection Q. Gx minus Gc is nothing but it is 0 minus 0, which is less than epsilon. Hence Gx minus Gc is less than epsilon for whenever x belongs to V delta C intersection Q. So by definition, epsilon delta definition of continuity, G is continuous. G is continuous at C. Okay, so G is continuous on, so that is G is continuous on Q. So in fact we have shown on the full domain. Okay, so you can take this function, you can define more functions like this. So you have to restrict your function, so you can, because this property has to be satisfied with the intersection domain, so we can take, so in this function is not continuous at anywhere in the domain, but the function G, which is the restriction of f on Q, is continuous on Q. Okay, so this is how we can have this result. So you can define functions, more functions like this as an example to this question, and you should try defining 3-4 different types of functions like this. Now let us go to the next question, which is question number 10. So again, this is very easy question. So you have to show that every absolute function is continuous on its domain. So you have to show the absolute function. So this is the question. So you have to show that fx equal to mod x is continuous at every point C in R. So this is also easy. You have to just use the reverse triangle inequality. So to let, we will start with any arbitrary point in the domain. So let C belong to R be any arbitrary point, and we will start with any epsilon. So let epsilon greater than 0 be any real number. So consider fx minus fc. So this is nothing but your mod of x minus mod of c, which is less than equal to mod x minus c. This is by reverse triangle inequality. By reverse triangle inequality. So this result is true using reverse triangle inequality. So you have got this x minus c is So now what delta you should choose? So let delta equal to epsilon greater than 0, then clearly by the choice of delta it is easy to see that fx minus fc is less than epsilon whenever your x minus c is less than delta. So this is following straight away from R, because this less than delta means this is less than epsilon, because delta is equal to epsilon. So hence f is continuous at C. Since C belong to R is arbitrary, it follows that f is continuous on R. So this is how you can prove. So these are all easy questions. Now let us take the next question, which is again easy question. So again this is an easy question. So you are given a function k greater than 0 and f is a function from R to R satisfying the condition fx minus fy is less than equal to k times x minus y for every xy belonging to R. You have to show that f is continuous at every point C belonging to R. Okay, f is continuous at every point C belonging to R. So you are given this condition, given fx minus fy, this is called Lipschitz condition, which you will study when you will study uniform continuity. So for now let us take this as a condition only. So fx minus fy is less than equal to k times x minus y for every xy belonging to R. So this we are given. To show f is continuous on R, so we have to show that f is continuous at every point in R. So let us start with any arbitrary point. So let C belong to R be any arbitrary point. Okay, and so because we have to show continuity, so we will have to take any arbitrary epsilon. So let epsilon greater than 0 be any real number. Now so we have to make use of this. So this is nothing but so delta we can choose directly from here, because we will get this x minus c and this is fx minus fc. So we can take delta equal to epsilon by k. Let delta equal to epsilon by k greater than 0. Now for any x belonging to v delta c, okay, so for any x in this, your x minus c, that is x minus c is less than delta, which is equal to epsilon by k. Consider fx minus fc, then by hypothesis this is less than equal to k times x minus c using hypothesis, using given condition. Okay, and this less than equal to k, this is k times epsilon by k, because your x minus c is less than epsilon by k, right? And so this is equal to epsilon. So you have shown that fx minus fc, so thus fx minus fc is less than epsilon whenever your x minus c is less than delta. Hence by epsilon delta definition of continuity, f is continuous at C. So we have shown that because C belong to R is any arbitrary point, so we are done in this case. Okay, now let us take the next question, which is question number 12. So this I have done in the class also, but for the sake of completeness I will do it here also. So we are given f is continuous on R. So we are given that f is continuous on R, and second we are given that f of R is equal to 0 for all R belonging to Q, and we have to show fx is equal to 0 for all x belonging to R. So this we have to show. So at rationals it is already 0, so we have to show that at irrationals also it is 0. So we will pick any irrational number. So let Cu belongs to R minus Q, that is C is irrational. Then by density theorem, whenever we have this Dirichlet type of function, we know we have to use this density theorem. That is, for irrationals also we have two sequences, one set of irrationals and one set of irrationals which converges to C, and for rationals also we have two sequences, one from rationals and one from irrationals that converges to C. So by density theorem there exists, because here we need only the set of rationals, so there exists a sequence xn in Q such that xn converges to C. So now we have a set of the sequence of rationals that converges to C. Now xn belongs to Q for all n belonging to n. This is this. So this implies f of xn is equal to 0 for every n in n, and this implies your f of xn converges to 0, right? Because it is a constant sequence, make it as star. Now since f is continuous at C and xn converges to C, so by sequential criteria for continuity, your fxn will converge to f of C. Okay, now by uniqueness of limit, because this here we have shown that it is converging to 0 and here we are showing it is converging to fc, so by uniqueness of limit fc is equal to 0. Okay, now since C belong to R minus Q is arbitrary, it follows that x is equal to 0 for every x in R minus Q. Hence fx is equal to 0 for every x in R, because we are already given that fx is 0 on set of rationals, and we have shown that fx is 0 on set of irrationals, so fx is 0 on every real number. So this completes this proof. Okay, so this is how in Dirichlet type of problem you will have to use this condition. Okay, now let us take another question. This is also Dirichlet type of question, so we will use almost similar argument what we use now. So we are given a function gx, so solution. So given gx is equal to, it is 2x when x belongs to Q and x plus 3 when x belongs to R minus Q, and we have to find all points of continuity when G is all points of continuity of G. So generally whenever we are given this Dirichlet type of problem, the points of continuity are the points at which these two functions intersect, that is points at which these two functions are equal. So we have to equate these 2 points, so you have to solve these two equations. Here it is very easy, here you can simply, but whenever you are given this type of problem, just equate the two functions. So 2x equal to x plus 3, so this implies what is your x is equal to 3. So you have to show that, so claim G is continuous only at x equal to 3. So whenever these two functions at points where these two functions are equal, only at that points the this Dirichlet type of problem is continuous, otherwise at all other points it is discontinuous. So this is what we have to show. So let us start the proof. So the proof is very simple. So we let C belong to R be any real number. So we will take it in two cases, when C is equal to 3 and when C is not equal to 3. Case 1, c is equal to 3, so we have to show that the function is continuous at this point. So to show continuity, we have to take any arbitrary epsilon. So let epsilon greater than 0 be any real number. So consider gx minus gc, so which is equal to, so gx is gx minus, so what you get when you put the value, so x is 3 is rational, so you get 6 here, in fact. Okay, so 6, so this is nothing but it will be 2x minus 6 if x belongs to q, and it is x plus 3 minus 6 if x belongs to q complement. So this can be simplified as, this can be written as this, 2x minus 3 if x belongs to q, and it is x minus 3 if x belongs to q. Sorry, there will be mod also, we have to put the mod also because we are starting with mod of this gx minus gc. So just put a mod here and mod here. So now both the functions are smaller than, definitely smaller than this, right? We can, because this is equal to this and this is smaller than this, right? Something positive, we are multiplying it by 2, twice of that. So is it fine? So this is smaller than this, and so what delta we should choose? Let delta equal to epsilon by 2 greater than 0. Then clearly by the choice of delta, gx minus gc is less than epsilon gx minus g3 whenever your x minus 3 is less than delta. Hence g is continuous at x equal to 3. So this is how you can prove continuity. So same steps will apply to any Dirichlet type of function. कुछ भी अगर Dirichlet type of दिया हुआ है तो you can just repeat this process. Now we have to show that g is not continuous at all other points. So case 2, c does not belongs to, c is not equal to 3. Now by density theorem, again we have two sequences. There exist sequences xn in q and yn in q complement. So by density theorem, there exist sequences xn in q and yn in q complement such that your xn converges to c and yn also converges to c. So for every real number, there always exist two sequences, one irrational and other in irrational, such that both the sequences converges to the same point. Now for all n belonging to n, xn belongs to q, yn belongs to q complement. So this implies f of xn is equal to 2xn and f of yn is equal to yn plus 3. So by algebra of limit of a sequence, f of xn will converge to 2c because xn converges to c, and f of yn will converge to c plus 3. So since c is not equal to 3, so this implies 2c is not equal to c plus 3. So this implies f of xn and f of yn converge to different limits, right? So by sequential criteria for limit, by sequential criteria for continuity, f is not continuous at c. So hence from the two cases, we conclude that f is continuous only at c equal to 3, right? Sorry, the function g. Okay, the function g. So we have g here at all points. Okay, so it is g, right? The function g is continuous or at only at c. Is it fine? Okay, fine. Yes. Now let us take the next question, which is question number 14. This is slightly trickier question, but it is similar to what we did for Thomae's function. If you look at the proof of Thomae's function, then it is the proof of this will be similar to that. So I would request, before pursuing this question, you should read the proof of Thomae's function, because we will be using the same technique here. So the technique used in proof of Thomae's function will be used here. Okay, so let us try to prove this. So we are given a function a to be the interval from 0 to infinity, and k is some function from a to r, and k is defined as, so k is a function from 0 to infinity to r, defined as kx is equal to 0 if x is irrational, and it is n if x is rational and x is of the form m by n, where m, the GCD of mn is 1. Mn are relatively prime to each other. Okay, so then we define kx equal to n. So we have to show, to prove k is unbounded on every open interval in A. Okay, so every open interval, k is unbounded on every open interval in A. So this is very simple. So what we have to do is, so basically, because you see we have to find, so to show unbounded, what we will have to do, we will have to take any real number or any integer, any positive integer, and we have to show that the value of k is greater than that value, right? If you take 1000, so then I can say that I will have the value of k to be 1001. If you will say that let us take 1 lakh, then I will say okay, then I can get you a number in that get your point in that interval whose image is greater than 1 lakh. So this is how you show that it is unbounded. Okay, so you take any integer, so let k belong to z positive be any integer. Okay, any positive integer. So we have to show that k, but let us take it m because it will confuse with the notation of k. So to show, okay, first we have to take any interval, because we have to show it on every open interval. So let I be any open interval in, say, A. Okay, so I is any open interval in A. Now what we have to do, we have to find a point in x in, so let, to show f, to show k is unbounded on I, we have to take, so let m belong to z positive be any integer. So we have to then, so claim is there exists x belonging to I in x belong to I such that kx is greater than m. So this will imply m is k is unbounded, because you you keep on increasing m, then we will always be able to find some x such that kx is greater than m. So that means the function is unbounded. Okay, so we have to find some kx greater than 0. So now what property we will use is, so let us, so for this what we will do is we will pick any 2 points in I. So let xy belonging to, yeah, xy, let us not take xy, let pq. So because I is any open interval, so we can choose any 2 points, because every open interval contains infinitely many points, so we can always choose two distinct points in. Let pq be any two distinct points in I with p less than q. Then then we know that the let s, so let us take this set, let s equal to this set x equal to m by n. So x is rational, so let us, x is defined, let us define like this. So set of all rationals intersection in the open interval pq such that x is equal to m by n and mn is equal to 1, and this n is less than equal to m. So we are collecting all rational numbers in this interval pq. We are collecting all rational numbers in this interval pq such that x is equal to m by n. Okay, x is equal to m by n and n is less than equal to m. Fine. We are collecting all the points, all the rational numbers in this interval pq where x is equal to m by n and n is less than equal to m. Fine. So as proved in Thomae's function, the cardinality of this set will be because any interval contains finite, any any bounded interval contains a finite number of this type of elements whose denominator is less than, they give a fixed number, because you can so claim cardinality of S is finite. And why it is finite? Because what are the possible choices for your M? So this P is positive, Q is positive, everything is positive, right? So M is less than equal to, so M is, because you want M by N to be, M by N belongs to PQ, you want M by N to be in PQ, that means M by N is less than Q. So if M by N belongs to PQ, then M by N is less than Q, so this implies M is less than N dot Q, and we want N to be less than M, so this implies this is less than equal to M times Q. So the maximum possible choice for M is this. Okay, so M has to be smaller than this number, so M is finite now and N is finite, so cardinality of S is less than equal to, because you have how many choices for M, so the possible maximum possible choices for M is, for M is M dot Q, and maximum possible choices for N is if Mn belongs to this intersection S and N is less than equal to M. Okay, so this is there. So maximum possible choice for N is M. So cardinality of S is definitely less than equal to m square times q. So that means S is finite, it cannot exceed this value, right? Because if m by n belongs to this set, that means m by n is less than q, that means n is less than equal to m, so your capital M is less than equal to mq. So how many choices for this? You have m dot q, and the number of choices for this is m, so S cardinality of S is finite. And now S is finite, so S is finite, this implies since q intersection pq is infinite, right? Every interval contains infinitely many rational numbers, is infinite, and S is finite. So this implies q intersection pq minus S is non-empty. In fact, this is also infinite set. So there exists, so this implies there exists x belonging to q intersection pq minus S. This implies x is equal to m by n, where mn is equal to 1 and n is greater than m. So this implies kx is equal to n, and which is greater than m. So hence k is unbounded. Okay, the proof is similar to what we did for Thomas result, right? In Thomas also we found we showed that this set has to be finite. So we were able to choose an interval in which there does not exist any point of this. Similarly, we are able here too we had to just find a point. So we are able to find a point in the interval PQ such that kx is greater than 0 and pq is contained in I. So we are able to find in each interval where there exists for a corresponding to each point m, each integer m, there exists x such that kx is greater than m. So k is unbounded. So let us take the last question of this exercise, which is question number 15. So this is also a bit trickier question. Okay, so we are given what we are given that f is a function, bounded function, f from 0 1 to R is bounded. Bounded means we can have supremum and infimum in the range set. Okay, and second, limit x tends to 0, f does not exist. Okay, so these two facts are given. We have to show there exist two sequences xn and yn in 0 1 such that both xn and yn converges to 0, but their corresponding sequences and the sequences f of xn and f of yn converge to different limit. So this is what we have to show. Okay, we have to show their existence, but we have to show that that these sequences converge, but they converge to different limit. Okay, so we don't have to show that they does not converge, but we have to show that such sequences converges, but they converge to different limits. So this is a little trickier question. So what we will do is we will so we have to construct this sequence xn and yn. So for that, what we will do is we will take, let for each n belonging to n. Okay, so first let m, because f is bounded, so let m equal to infimum of fx, x belonging to 0 1, because f is bounded. Yes, so this set is bounded, so infimum and supremum will exist, and this capital M equal to supremum of fx, x belonging to 0 1. Now for each n belonging to n, let in equal to, for each n belonging to n, let in equal to 0 to 1 by n. So we are considering this subset of this 0 1, right? So this is contained in 0 1. Now what we will do is we will define two different sequences. So what we will do is, because we have to take this, so we will define, so let what notation choose we should choose, yes, let an equal to infimum of fx, x belonging to in, and bn equal to supremum of fx, x belongs to in. Okay, so again f is bounded, so this infimum and supremum will exist, so we can take this. So an is a sequence such that an is the infimum of fx over in and bn is supremum of fx over in. So we have two sequences now. Now since, so clearly by definition of supremum and infimum, what we will have, m is less than equal to an, and an will have to be less than equal to bn, and bn will have to be less than equal to m for all n belonging to n. So that is, the sequences an and bn are bounded sequences. Okay, so these two sequences are bounded, right? It is bounded below by m and bounded above by capital M. So bounded sequences, they are bounded sequences because your function is bounded, so because of that we are getting these two sequences to be bounded sequences. Now we will show that these are monotonic sequences. So this is true because since in plus 1 is contained in in, right? The way we have chosen in is 0 to 1 by n, so in plus 1 will be 0 to 1 by n plus 1, so that will be contained in in. So infimum of a larger set is smaller than the smaller set, so an is less than equal to an plus 1, right? And bn plus 1 is less than equal to bn, right? So larger the set, larger is the supremum, and smaller is the infimum, right? So this is true. So this implies for every n this is true, for all n belonging to n. So this implies an and bn are monotonic sequences. Okay, so an and bn are monotonic sequences, and they are bounded, and bounded also, yeah, you can say bounded monotonic sequences are bounded monotonic sequences, and every bounded monotonic sequence are convergent, right, by monotone convergence theorem. So by monotone convergence theorem, an converges to say a and bn is converging to b, right? So both are monotonic bounded sequences, so both are converging. So now an converges to a, bn converges to b. Also, but because of this result, since an is less than equal to bn for every n in n, so a will be smaller than bn. Since an is less than equal to bn for all n belonging to n, so this implies a is less than equal to b. Okay, fine. So this is how we have defined it. So mark it as star. Okay, mark it as star. Now let us come back to, because we have to generate two sequences xn and yn. We have not done that. We are going to use an and bn for that. So we have to generate xn and yn, two sequences. Yes, so how we will generate these sequences? So we will use the definition of supremum and infimum. So since for all n belonging, yeah, Now for each n belonging to n, an is less than an plus 1 by n, right? And bn is greater than bn minus 1 by n. So this being infimum, so this is not infimum, this is not infimum, that means there exists some xn belonging to in such that x. So then by definition of infimum and supremum, this number is greater than the infimum, so there will exist something which is smaller than this. By definition of infimum supremum, there exists xn yn belonging to in such that an will be less than equal to f of xn, which is less than equal to an plus 1 by n, right? And bn will be greater than equal to f of yn, and this will be greater than bn minus 1 by n, because this is not supremum, so something will be bigger than this, and this is not infimum, so something will be smaller than this, right? So because of this infimum and supremum property, so we have generated now two sequences xn and yn. So clearly, because xn belongs to in, so that is both xn and yn, xn is 0, since xn belongs to in and yn belongs to in, so this implies 0 is less than xn less than 1 by n, and 0 is less than yn less than 1 by n for all n belonging to n. And what does this imply? This implies your xn converges to 0 and yn converges to 0. So then xn converges to 0 and yn converges to 0. Okay, so now we are able to generate two sequences. What we were required to generate two sequences xn and yn in 0 1 such that xn converges to 0 and yn converges to 0. So we are able to generate such sequences. Now where will f of xn will converge? From this. Okay, so we can make it, what we can do here is we can get this a little down and we can write here, because our an, this is fxn is less than, is lying between an plus 1 by n for every n. So by because this is converging to a, right? This converges to a and this converges to a. So this implies limit n tends to infinity, an is less than equal to limit n tends to infinity f of xn, or we can simply say by squeeze theorem, right? Or let us just simply say by squeeze theorem, by squeeze or sandwich theorem, or sandwich theorem for sequence, limit of sequences, for sequences, sequence wali squeeze theorem we are applying. So f of xn will converge to a and f of yn will converge to b. Mark it as double star and mark it as triple star. So now we are able to generate two sequences xn and yn both converging to 0 and their corresponding functions are converging. So they are converging, we are only left to prove that their limits are unequal, right? We are only left to prove that the limits are unequal, they are converging to different limits. So we have to show that a is not equal to b. So claim a is not equal to b. So suppose, if possible, a is equal to b. So that is an is converging to a which is equal to b, and so bn is converging to this, right? So both are converging to the same limit. An is converging to a and bn is also converging to a. So now we have to prove this. So in this case we will show that limit x tends to 0 fx will be equal to a, which is will equal to b. So basically we will show that limit exists, which will contradict our given hypothesis that limit does not exist. So this will be our contradiction. So we'll show that limit exists. So for this we will start with any epsilon greater than 0. Let epsilon greater than 0 be any real number. Okay, so now then, because an is converging to a and bn is converging to b, so there exists m1 m2 belonging to z positive such that an minus a is less than epsilon for all n greater than equal to m1, and bn minus b is less than epsilon for all n greater than equal to m2, right? So this implies so what does this imply? This implies, so let m equal to maximum of m1 m2, then what we have is an minus a is less than epsilon and bn minus a is also less than epsilon, because a is equal to b for all n greater than equal to m. Since a is equal to b, so we are replacing b by a. So now so we have to show that limit x tends to 0 fx is equal to a. So what we will do, we will have to find some delta such that fx minus a is less than epsilon whenever x minus 0 is less than delta. So what we will do is we will take delta equal to, because delta should depend on this m, so what we will take, so let delta equal to 1 by m, which is greater than 0. Okay, so then x minus, now let x belongs to v delta c, v delta 0. So this implies mod x is less than delta. So this implies your, because x v delta intersection a, right, f is defined on a 0 to infinity. So this implies x is less than delta because x is positive. So you can have this x is less than delta. This implies x belongs to, x is less than 1 by n, right? X is less than 1 by m. So this implies x belongs to in for all n greater than equal to m, right? So this x belongs to in for all n greater than equal to n. Now x belongs to in and alpha n is infimum of in and beta n is greater than in, supremum of in. So fx will lie between these two. So then this implies alpha an is less than equal to fx is less than equal to bn for all n greater than equal to m. Why this is so? Because your x belongs to in, x belongs to in, and alpha an is infimum of f of in and bn is supremum of f of in, okay, for all n greater than equal to m, right? So this is there. Now what we will do, we will subtract a from all sides. So this implies an minus a is less than equal to fx minus a is less than equal to bn minus a for all n. Now if you will see this, so this interval implies that minus epsilon is less than equal to an minus a and this is less than equal to, so mark it, so mark it as capital A. So then from A what we will have, so from A it follows that minus epsilon is less than an minus a and an minus a is less than equal to fx minus a, and this is less than equal to bn minus a, and this is less than epsilon for all n greater than equal to m. So this implies your fx minus a is less than epsilon. So hence, because we started with any x satisfying this property, v delta c intersection a or v delta 0 intersection a, so this implies fx minus, hence fx minus a is less than epsilon whenever x belongs to a intersection v delta 0. And what does this mean? This means that limit x tends to 0, fx is equal to a, contradiction to the given hypothesis that limit x tends to 0, fx does not exist. So we were given that limit does not exist, but we are able to prove that limit is existing and equal to a, so our assumption is wrong. So hence our assumption that a is equal to b is wrong, thus a is not equal to b, and hence the proof, because we are able to generate two sequences, right? So we are able to generate two sequences, xn and yn. So we are able to generate two sequences, xn and yn in this, so xn and yn in in, such that xn is converging to 0, yn is converging to 0, f of xn is converging to a, f of yn is converging to a, and a not equal to b. So this was the desired thing, so we are able to prove this. Now what next we are asked to prove? We are, so this completes the proof of this theorem. Okay, so this completes our exercise 5.1. In our next video we will solve exercise 5.2. So thank you everyone for watching this video. Bye everyone, have a good day.
Thank you for watching this video. Please subscribe to our YouTube channel, Online Learning, to stay updated and share with your friends. Happy learning through online learning. To watch more, click on any of these cards. Thank you once again.